So previously, in previous session, we have discussed some of the part of SPI protocol, introduction to SPI, and what is meant by SPI interface, how it works, the features of SPI, and all. So if you miss that session, just I will share you the YouTube link of part 1. You can go through the part 1 session. Okay, that is only theory. Today we'll discuss on SPI protocol, main feature of SPI protocol, how it will work, mainly the clock polarity and the clock phase. Okay, if you don't have any protocol knowledge, what is mean by protocol and all, no need to worry. When we discuss the end of the Verilog session, we can discuss what is mean by protocol and all. If you just have the idea, just you can have the session. Okay, so yeah, today we are going to discuss the SPI protocol. Okay, first of all, what is mean by protocol? It is nothing but the communication purpose we will use. Okay, to device communication purpose, it is a set of rules we need to follow to communicate between two devices or two components. For that purpose, we will use the protocol. Okay, in that way, we have several types of protocols like UART, I2C, SPI, AMBA protocols, the parallel communication protocols like AMBA protocols and all. Okay, so if you miss all these things, I will share you the part 1 link. Just go through that session today or tomorrow, so that this part you will understand. Okay, so coming to the SPI protocol, this is the serial peripheral interface protocol. Okay, same like a I2C protocol. It is a serial communication protocol. Compared to the I2C protocol, SPI is mainly used, okay, because it is a full duplex communication protocol, okay, and also work for the high speed communications. So it is a full duplex in the sense both the transmission and receiving can be done at a time. Remaining protocols are half duplex, right? So once the master is in transmitting, the slave must wait until transmitted completed. Okay, then it can receive the data. So it is not a bidirectional. But whereas a SPI protocol, it is a multi-dimensional. I mean bidirectional. Okay, it is a full duplex. So SPI, it works on the under the synchronization. Okay, it has the synchronization. Whereas a UART protocol, it is a asynchronous. We will use the baud rate for the synchronization purpose, right? But here in I2C and SPI protocol, we'll use the clock for synchronization purpose, and we will use the rising edge and the falling edge of the clock pulses. Okay, to sample the data and to shift the data. And the the SPI protocol interface has the 3 wire or a 4 wire. It has a 3 wire or a 4 wire. Okay. So here mainly we are focusing on the 4 wire SPI interface. Okay. 4 wire in the sense there is a master and there is a slave. Okay. What is the master? Master initiate the transfer. Okay, it send a request, everything. It initiate all the transfers to the slave. Okay, slave will take the whatever the transfer data or there, it work according to the master. Okay, that is mean by slave. Nothing but it is a transmitter. It is a receiver. Okay, so it has a 4 wire. We can call it as a main. Okay, we can call it as a main, and here we can call it as a subnode. Okay, single master, single slave. In SPI protocol, we can connect with single master with multiple slaves. Okay, so we already know in I2C concepts, we have seen multiple master and multiple slave. If we have multiple master and multiple slave, you can take a single master by using the arbitration concept. You can select any one of the master, and from that master you can send the slave. Okay, you can select the slave. Okay, same here, a single master, multiple slave. Okay, one master can be connected with the multiple slaves in a normal manner or a daisy chain fashion. Okay, those things we'll discuss in the end of the session. So here we can use the multiple slave. Here, if you see, This is SS or CS. We can call as a chip select. Okay. We can call it as a chip select. It is a active low signal. Active low signal means whenever it is a low, then only the circuit will be activated. Okay. So this is an active low signal. It should be zero. Then only all the cases will work. And another thing is master out, slave in. And here master out, slave in. MOSI is the master out, slave in. We already discussed all these things briefly, right? So master in, slave out. Some of the new students are there, right? So that's why I'm discussing. So master in, slave out. So these are bidirectional. Okay. No, both can transmit at a time. Full duplex. And here we are using the serial clock. Okay, so this is the SPI protocol, which has the four signals. So mainly SPI protocol means it has these MOSI and MISO data lines. MOSI transmits the data from master to the slave, and MISO transmits the data from slave to master. Okay, this is the chip select signal is mainly used for select the slave. This is normally an active low signal and is pulled high to disconnect the slave from the SPI bus. Okay, so these are the things mainly. And data transmission in the SPI protocol. Okay, how the data will be transmitted in the SPI protocol means the main is the clock signal, and the it should select the slave signal. Okay, it should select the slave signal by enabling the chip select signal. Okay, so usually chip select signal is an active low, as we said, and SPI is the full duplex. So both main and subnode here. Main and subnode can send the data at the same time via MOSI and MISO. Okay, so the during SPI communication, the data is
Excuse me, ma'am.
simultaneously
Ma'am, one
transmitted.
doubt.
Yeah.
Now, what is this? What is the difference between this serial clock and normal clock we use?
Single clock and not. This is just serial clock, not single clock. It is a serial clock. That means nothing but we are using the serial communication here, right? That's why it just pronunciation like a serial clock. Whereas I2C also it is a serial communication protocol. So it has a two lines, right? Two signals like a serial clock and a serial data. That is just like pronunciation. If we see APP, AHP, the signals will start with a P for APB, H for AXI. Okay, like that.
Ma'am, so can we connect the normal clock to that serial clock only, or this is different from that clock?
No, it is same clock. Both are not different. Just it is a clock. Okay.
Okay.
Yeah. Okay. So during the SPI communication, the data will be transmitted simultaneously. It is shifted out and serially into the MOSI or serial data out bus. Okay, and also receive the simultaneously the data on the bus, whatever MISO is there, it will sample and read it simultaneously. Okay, so mainly
This SDI and SDO is nothing but MOSI and MISO of slave.
yes, sir. Mainly it
Okay.
depends upon the MOSI and the MISO. Okay. Here MOSI in the sense a master out slave in, which is transmitting to the SDI. SDI is nothing but serial data input. Sorry, slave data input. SDO is nothing but slave data output is sending to the master. Here the signal is master in, slave out. Okay.
Okay, ma'am. So basically, SDI is our MOSI and MISO. SDO is our MISO for the slave.
Yes.
Okay.
Okay, so this is the main SPI configuration. And if we see the clock polarity in and the clock phase, suppose in I2C, if we see I2C have the frame format, okay, there will be one frame format and there will be, suppose if there will be start condition and there will be stop condition. Start condition and stop conditions depend upon the serial clock and serial data. So I will share you a video that also just you can go through that video. You will understand how I2C frame format. Like that, every protocol has some frame format. Yacht has some frame format. Total 11 bits will be there in yacht. Start bit and stop bit. In middle, there will be address and data parity bits like that. If you go to AMBA protocol like APB, it has some other like finite state missions. It has some finite state missions, some read cycles and write cycles. Like transmitting data and reading data, there will be some clock, waveforms will be there. So like that, for the SPI also we have the clock polarity and the clock phase. These are the main signals. If you see CPOL and CPHA. Okay, CPOL in the sense clock polarity, CPHA in the sense clock phase. Okay, and SPI has 4 modes, 0 to 4 modes. So based on these 4 modes, we are going to sample the data and shifting the data. Okay, and also by using these 4 modes, we are writing the program. Okay, we are taking these 4 as a main thing and generating the master and generating the slave. Okay, so these all nothing but the master. Okay, master need to send the SPI mode. It should select the SPI mode. It should generate the clock polarity and clock phase. Okay, so based on those, the data will be sampled and data will be shifted. Okay, so these things need to generated by master. So we'll see what is mean by these all things. Okay, so CPOL, CPHA means 2-bit. 2-bit in the sense we'll have 4 combinations. Okay, so 00, 01, 10, 11. So if SPI mode is a 0, then both are 00, then we are telling clock polarity in ideal state is logic low. Is it logic low? So if you see how the clock phase used to sample or how the data will be shifted. If clock polarity is 0 and clock phase also 0, the data will be sampled on the rising edge. Okay, the data will be sampled on the rising edge of the master to slave and shifted out on the falling edge. Okay, it will be shifted out to the falling edge. And for 0, 1, the data will be sampled on the falling edge and shifted out on the rising edge for the mode 1. For mode 2, CPOL is 1 and CPHA is 0. It is a logic high. The clock polarity is logic high. So data sampled on the rising edge and shifted out on the falling edge. That is one case. And if SPI mode is 3 and CPOL and clock phase both are 1, 1. So clock polarity is high and the data sampled on the falling edge and shifted on the rising edge. Okay, so these things we will see now how the waveforms are looking like. So this is the condition first case. Okay, so when SPI mode is a 0 and CPOL is 0, CPHA is 0. So clock is ideally low state. Ideally low state in the sense initially it is a low state. Initially the clock will be started with a logic 0. Okay, so if you see here NCH is the chip select. Based on the chip select we are going to select the slave. So it will be always active low signal. So it should be in 0. Okay, whenever it is 0, the actual functionality will be happen. Okay, the operation will be performed that time. Otherwise, it will be in a high impedance state or an unknown state. Okay. So first clock, initially what it is telling, ideally low state. You can go back and you can check. Okay, if 0, 0, clock polarity ideal state is a low state. So clock is generating with the active here with the low state. So if you see here, mostly we are transmitting some data 1 at the clock high. Okay, at the clock high, we are transmitting the data. So at the rising edge of the clock, the data is sampling. Okay, so the data is sampling at the rising edge of the clock, and at the falling edge of the clock, if you see, this is the falling edge of the clock. At this time, the meso is getting the data. Meso is getting the data. Shifting is nothing but transmitting. Okay, master to slave. It is transmitting the data. Okay, so Morsi is nothing but sending master to slave. Meso is nothing but master is the input, slave is the output. Slave is receiving the data. Okay, so just a second. See, Mosi in the sense, from the master, you are sending the data to the slave. Miso in the sense, from the slave, Miso, it is receiving the data. Same thing happened here. Okay. So if you observe, Mosi 1 at the rising edge, the data is sampling, and the falling edge, the data is shifted. Same at the rising edge, again, data is sampling and falling edge shifting. Orange color is sampling the data. Blue color is shifting the data. Okay. So that is for case
Ma'am,
1.
means when the data, how we are sampling and shifting the data.
That depends upon the programming and all. Okay, how we will sample the data and shift the data through the programming, we'll write those things. Okay.
No, ma'am. My
But,
question is, the Mosi is master out slaving means it is sending the data to the slave, and
yes,
Miso is receiving the data from the slave.
yes,
Okay, so 1010 is the another data, as you say, as you said, this is a type of the full duplex. So at a time, our master can transmit as well as receive the data.
yes.
But here only the data that we are sampling will be shifting at the next clock pulse.
See,
So
if you see half duplex, it will be not like this. Okay, at some time the master is sending to the slave. After completion of that, all the bit transfers, then slave will receive. This will be the condition. It may be 8-bit size. Suppose if it is 8-bit size means first it will transfer all the 8 bits, then only slave will receive the 8-bit totally. But here, if you see in SPI, it is not like that. It is sending one bit, receiving one bit, sending one bit, receiving one bit. That means all things happening in a full duplex manner.
ma'am, as suppose at the rising edge, Mosi means master is sending one bit to the slave. Okay. So is it necessary that slave will also send the same data at the next pulse to the master?
Yes, sir, that is only the protocol in the sense transmitting the data. Okay, we are just transmitting the data from one component to another component. We should transmit same data between two components, just by using some of the protocol. Okay, some of the rules and regulations we need to follow.
Okay, means if Mosi is sending suppose 1010 pattern, then the
Yeah.
slave will also send the same pattern 1010 to the
Yes,
master.
yes.
Okay.
Maybe it may be the master or some other component it may connect. See, this is one master, this is another slave. Here, no need to send again to this master. It may send to some other component. Some other slaves will be connected in the in the motherboard. If you see, the connection will be like this, right? So internal connections, like it will be
So
like this.
ma'am,
So it is transmitting one master to the another slave or master. Yeah.
ma'am, what's the meaning of sending the same data again to the master that it is sending to the slave?
That's what I am telling. It will not send like this again to the same master. It may connect to some other masters.
Okay, means this
What
meso
is
pin.
meant by protocol? This is one component and this is the second component. Whatever we are receiving the data from a previous component or some previous circuit, some processor and all, the data we are transmitting to overall the motherboard. Okay, but here this processor may be accepting parallel data and here it is accepting the parallel data, but these components, internal components may not accept the parallel data. These may accept only serial data. For that purpose, we are just taking the protocols and we are converting the parallel data into serial. And this here we are using the SPI or I2C protocol. Okay, for these communication purpose.
Okay, and ma'am, so can you please repeat what's the meaning of full duplex? Because what I have read is full duplex means the receiver or transmission in between the those lines, both sending and receiving of data can take place.
Yes. Yes.
Okay,
See,
but
okay.
here no ma'am, but here we are only transmitting the data, I think.
Not only transmitting the data, here it is receiving the data. MOSI means transmitting the data. MISO means receiving the data. Okay.
Okay.
Um, just a second. Which I can show. Okay, wait. I will show you the APB protocol.
Okay.
I just added you here. I know you don't know these things. See here, this is the APB protocol. Okay. APB protocol is a half duplex communication protocol actually. Half duplex communication in the sense here, suppose write data. This is the write data. What is the size of this write data? Is a 8-bit size. Okay. Once total 8-bit size data has completed writing, at the write is the sense a master to slave. Okay. Once it completed writing the data, all 8-bit, then only here slave is accepting the data. If you see here, slave is ready to read the data here at a time. Okay. But here, if you see SPI protocol, what happens? At a time, we are not
Okay.
sending the
Yes,
data,
ma'am.
right?
Yes, ma'am.
One bit,
Yes, ma'am. Now about
one bit, one
yes,
bit,
yes.
one bit, one bit, one bit. Okay. So
So
that
ma'am,
is
means in AMBA protocol, as it is a single duplex. So for the suppose T1 time, it will send the data completely for 8 bits, and then for the T2 time, the slave will take the time to acquire the data, to receive the data, right?
um that mean here it is sending all the 8 bits at a time, but here it is not sending at a time. You are telling
Okay,
same like
okay, ma'am. Yes, ma'am. Yes, ma'am. Now, got it.
okay. So this is a case one. Okay, for CPOL and clock phase and the clock polarity for 0, 0 case, how we are transmitting the data and receiving the data. Suppose if we take 0, 1, okay, no need to take all the phases at a time, all the modes. Just we can write in any of the mode. SPI have the 4 modes. We can utilize any one of the mode. By using a single mode, we can write all the programming of SPI. We can develop any by using any mode, but we need to know all the things, right? Just for, that's why. See, for 0, 1, polarity is 0 and phase is 1. Okay, in that what happens? Phase polarity is a 0 in the sense clock ideally it will be in the 0 state. Okay, so this green is nothing but chip select is active low at that time, so that it will done the operation. Okay, so in that case, what happens? The data will be sampled on the falling edge and shifted on the rising edge. Okay. So here this is the shifting. Blue color is the shifting here on the rising edge, and here orange color is the falling edge. That means data is the sampled at that time. Okay, data will be sampled at the orange color and shifted at the red color, blue color. Okay, so that is a one phase.
Okay. Means opposite of the what we have read in the first
Yes.
case.
Yeah.
Okay.
So next case is both are 1-1. 1-1 in the sense clock polarity is starting with a clock high. Okay, initially ideal state is a high. Once a chip select is also 0, then it will be start condition is here. Once clock is high and chip select is high, once data is ready to transmit some data, so the data is sampled on the falling edge. So here at the falling edge, the data is sampling and shifted on the rising edge. So here the data is shifting on the rising edge. Okay. So that is another thing, clock polarity. Next, same here, 1-0 condition. Polarity is 1 and phase is 0. So here clock initially started with the 1 and the data is sampled on the rising edge here and shifted on the falling edge. Okay, getting at the falling edge of the clock to the MOSI and the MISO. These are the 4 conditions. According to these 4 conditions, we can develop the program. Okay. Next thing is a multi-node configuration. Multi-node configuration in the sense one master, multiple slaves here, right? So if you have one master, multiple slaves, we can connect in a regular SPI mode or we can connect in a daisy chain fashion. Okay, you know the difference between scan chain and daisy chain. Scan chain is
Yes.
nothing but regular mode.
No, ma'am.
Daisy chain, in the sense, I will tell you. So regular mode in the sense, if there are three type of three type of slaves. This is the slave 1, slave 2, slave 3, or you can call us as subnode. Okay, so this slave has one select chip select. This slave is connected to another chip select, and the slave is connected to third chip select. Okay, this is normal regular, like the master has the multiple chip select. We can select any of the slave, and normal all these signals are same. But if you take the daisy chain fashion, daisy chain means it will look like this. So SPI main has only one chip select. This chip select will be connected to the first slave. From the first slave, SDI output will be connected to the SDI input of the next slave. Actually, this should connect the MISO and this should connect the MOSI. But internally in the daisy chain fashion, one slave will be connected to the another slave and this slave will be connected to this slave and finally the third slave will be connected to the MISO. Okay, so this is how we take the daisy chain fashion. Have any doubts up to here? This is main thing of SPI protocol, and not only this, we already discussed part 1. I will share you. And clear up to here, everyone. Mainly, who is this? What is his name?
Ma'am, here we can have only one master and multiple slaves and not the opposite.
Suraj Yadav. Is it clear for you?
Ma'am, am I audible?
Yes, tell. Kirti, tell.
Yeah. So here, in the last two slides we saw, we have one master and multiple slaves. Is that the only possibility, or we can have multiple masters?
No, for SPI, we don't have multiple master. We'll have only one master, multiple slaves.
Okay.
For I2C, we have multiple masters and multiple slaves. So there we will use the arbitration concepts. If you have multiple masters in SPI, you can also use arbitration concepts here. Okay, we'll discuss arbitration concept when we discuss the I2C protocol. Okay. Arbitration is nothing but just if we have multiple masters like that, master 1, master 2, master 3, we will send some bit 1011, some number of bits we'll send, and based on the AND operation or NAND operation, we'll select any of the master and we'll disable one of the master. So finally one master will get activated and it will on the bus and it will transmit the data. Okay, that is arbitration concept if we use the multiple master. But here we are not using multiple master. SPI, we don't have multiple master. Okay.
Okay, ma'am.
Okay. So any other doubts? Okay. We'll see the programming, how to write the program for this. So first we'll write the module for the SPI protocol, SPI master. And another thing, who is this guy? Fanish. This is just I added for this session. Okay, this is actually it is not meant for you. This is separate session for other guys. I just added you to know the things. Actually, SPI protocol is not in your schedule. Okay, like in your course content. But you will
No
know
issue.
the thing, right?
Yes, ma'am.
So that's why
Yes,
I
ma'am.
just
Yes, ma'am.
added you in this
Okay.
session. And you no
Okay.
need to worry. I will complete all the things accordingly. Okay.
Okay. Okay.
Yeah. So see how to write the program for SPI. Suppose here SPI master. Module SPI master. And here parameter SPI mode. We have different number of modes, right? SPI mode 0, 1, 2, 3. Like that SPI mode parameter equal to 0. And clock per half bit is equal to 2. Like we have taken clock per half bit. That means two number of bits. Okay. So either 0 or 1, 2 bits we are transmitting, right? So 2 bits we have mentioned here. And input, this is the main reset and clock, input, reset and clock. And this input is a byte to transmit on MOSI. Okay. Total 8-bit data we are transmitting, right? So 1 byte. And input dB, this is nothing but data valid pulse. Okay, pulse signal with whatever we are transmitting the byte here, that dB. And output is the ready, transmit ready for next byte. This is nothing but ready. Okay, 1 byte is completed. Next byte we need to transmit, right? So to check that thing, we just taken the ready signal. And next, at the receiving side, this is data valid pulse for the receiving signal for 1 clock cycle. And this is for receiving the data, main data. Okay, MISO data. That is output for MISO. And these are the SPI interface signals like clock, MISO, and MOSI. And we have the clock, we have taken this as a clock as the output to the master, and MISO is the input to the master, and MOSI is the output to the master, right? So based on the master, because we are constructing the master here, right? Based on the master, we need to take the these signals. Okay. Can you please join for the next session, everyone?
Yes.
Okay, ma'am.
Quickly. Next, wire clock polarity and clock phase, these signals. And we have taken the counter, clock count. Okay, it is just to count how many number of clock cycles it required. Okay, clock per half bit we are transmitting the data, right? So it will take how many clock cycles are required to count the clock cycle. Actually, in the I2C or APB, how we will take the count is just we are taking 8-bit of data, we are transmitting the 8-bit of data. So automatically the count size will be 8-bit data. Will take automatically count bit size is a 8-bit data. But here we are transmitting with respect to clock at a time, right? So if you see, can you tell me what is this $clock2? What is mean by function $clock2 in Verilog system task? It just return the ceiling of log. Okay, log2 for the given argument. It is just a ceiling. Okay. Ceiling is in the sense a round off. Okay. So suppose if you take any 15 number of combinations. Okay, 15 number of combinations means 4 bit. 4 bit, right? So automatically it will generate like a 4 bit. It will round off to the 4 bit. Okay. So that's why here we are using a $clock2. So clock per half bit into 2 minus 1. What is a clock per half bit? 2 bits we have taken, right? So 2 into 2, 4 minus 1, 3, 3 down to 0. Total 4 bit. Okay. So that is the clock size here. You can directly take 4 down to 0 also. No need to write all the things. But if you want to write some in different way, this will be the good coding style. Okay. So when you are practice, then only these things will get. Okay. So that is the count, clock count. And this is the SPI clock, temporal
Ma'am,
clock.
what is that $clock2 for used for?
Yeah, that is a ceiling for logarithm. Like it will convert to the suppose if you take number of combinations. Okay, so you don't know how many bits it required. You just know how many number of combinations are there. Suppose there is a 15 number of combinations. If you want to generate 15 number of combinations, how many bits it will require? 4 bit required, right? So this thing automatically it will convert into the bit manner. Okay.
Okay, ma'am.
Yeah, if you don't write this also, no problem. Directly in this place, you can just put 3 down to 0. Okay. It is not a problem. Just that is one different thing. And here SPI clock edge is also important because we are seeing positive rising edge doing something, falling edge doing something like that, right? So leading edge, trailing edge also we need to take. And this is a receiver transmitter DV and byte and receiver side count and transmitter side count operation. Okay, so I will share you this code also. If you see here, it will be looking confusion in single time. So I will share you once you can go through that, you will understand clearly. Okay, next assign clock polarity is equal to SPI mode equal to 2 or SPI mode equal to 3. SPI mode equal to 2 or SPI mode equal to 3. Based on these two OR operations, CPOL will be allocated. Okay. So if SPI mode equal to 2, what is the CPOL for SPI mode equal to 2? You can check here. SPI mode equal to 2.
It's
CPOL
1.
is the 1. Okay. So 1 plus SPI mode equal to 3. What is CPOL? Again 1. So 1 plus 1 is a 1, right? So that 1 will be assigned to the polarity here. Okay. Next, assign clock phase. So SPI mode equal to 1. Then what is the clock phase? SPI mode equal to 1. Then clock phase is 1. Another thing, SPI mode equal to 3. Then what is the clock phase? SPI mode equal to 3. Here also clock phase is 1. So 1 plus 1 clock phase is equal to 1. Okay, so that you can check for polarity and the phase. That means we are selecting only one case here. Here we are selecting polarity one case and phase one case by using that conditions, or directly you can assign 1 1. Okay, so this is a different case. We are assigning 1 1. And next, all so
That
here,
is, we are using one mode only for hard coded mode. Okay.
yes, you can
Right.
use one mode. Yeah, here we are using only one mode. If you want to use like 2 3 modes, you can write the program accordingly. Okay. Next purpose, generate SPI clock correct number of times. Suppose here, just we are generating initially the steps when we write the any program, any protocol and all. First, we need to write for reset. Okay. So here we are also doing the same thing. Always at the rate of posage clock, I clock, or negate, I reset. Further, if reset is high, these all signals are getting 0. If reset is high, all are getting 0. SPI clock is getting a CPOL. The default, assign the default state to the ideal state. Okay, CPL so clock should get the ideal state, right? How it will get ideal state? Based on the CPOL. Okay, based on the CPOL 0 and CPAH, based on that the clock will go to the low state, right? So that's why we are assigning CPOL to the clock. Okay. And next one, default assignments, leading edge and trailing edge also 0 0. Next,